Okay, now for our example here, let's take a look at RAID 0, and that's going to be disk striping. Now, RAID 0 is given the number 0 basically because it's not really RAID in the fault tolerant sense. It gives us an increase in performance because we're now going to write the data in two places. So that part's good, but as far as actually being able to recover the data if something were to go bad, if one of these drives were to fail, no, it doesn't give us any fault tolerance. But what's happening here is this. With disk striping, RAID 0, we have the ability, rather than writing all of the data to one drive, we can split that between two drives simultaneously. So let's say we're striping in 64K chunks of data. Okay, well, without RAID, we'd have to write the entire 64K to one drive. Or let's actually make it a bigger file. It might be a little easier to digest here. Let's say we have a 512K file. If this were a single drive, we'd have to write all 512K consecutively, and we have to just go from start to finish. However, when we're striping, if we're using a 64K stripe, we can write the first 64K to here, and then almost immediately start to write the second 64K here, and then the third 64K here, and the fourth 64K here. So in doing so, we're able to almost write at exactly the same time. We have to first initiate the write here before we can initiate the write on the second drive, but you get the idea. It's in effect doubling our throughput. So it gives us an increase in performance, and this is really liked or used quite a bit by gamers and hardcore speed enthusiasts just because of the speed increase. However, like I said, if one of these drives were to go bad, this one went belly up on us, well, we cannot recover the information on that drive. So it's better to use, if we're going to move into a fault-tolerant method, either use one of the other two methods of RAID, and that's going to be RAID 1 or RAID 5. Okay, now the next one would be RAID 1, and that's going to be disk mirroring. And with disk mirroring, basically what we're doing is mirroring one drive to the other. So if we have, or whatever gets written to this drive, would then turn around and be written to this drive. So as you can imagine, there is no increase in performance per se. However, we do have the added reliability or the bonus of having our data duplicated. So within our operating system or on a hardware controller, we'd set up disk mirroring. If in fact one drive were to go bad, we would simply quote-unquote break the mirror, tell the operating system which one to boot from. So let's say this was our boot drive normally. Well, we'd break that mirror and then point it to this drive. So now it would boot from the backup copy. Then we could go replace this drive and rebuild the mirror. In effect, it would just copy all the data from this drive to this drive. Now, one thing again worth noting is when we have serial ATA, one of the added benefits of a serial ATA setup is that we have hot swappable drives. Now obviously you can't hot swap your system drive because your operating system's on that, but if you had several other drives sitting in here, you could, if one were to go bad, you could pull that drive out while the system's up and replace that drive. It doesn't necessarily have, you don't necessarily have to shut your system down. Okay, now for the purpose of our discussion, let's assume that here we have disk mirroring. Both of these drives are operating off the same SATA or serial ATA controller. Okay, so recall, we could in fact drop a serial ATA card into our system. And again, if we did that, again, we'd have them both coming off of the same serial controller card. Okay, so this is our SATA controller. However, we could put in two separate controllers, and if we did that, we would have one drive sitting off of here, and then one drive sitting off of here, both of which would be mirrored. But now instead of having one controller basically do the work of two, writing data to two separate drives, we could have two controllers. So that way, if one were to fail, we could just continue on with life as normal. And we would also get roughly the same type of speed increase, because rather than having one controller having to write to two locations, we'd have each controller writing to just one drive. So it wouldn't give us quite the same performance as the old one controller, one drive setup, but it gets close to it. And it also gives us the added benefit of mirroring our data, like I said, so if one drive were to go bad, we don't lose everything. Additionally, when we use two controllers, one for each drive, that's referred to as disk duplexing. So you have disk mirroring, which is one controller for two drives. Disk duplexing, same concept, mirroring the information. It's just two controllers, one for each drive. Okay, so let's take a look now at RAID 5, which is disk striping with parity. Now I have the controller card, the serial ATA controller card, sitting here, and I have 4 hard disks, 1, 2, 3, and 4. I didn't draw the cable all the way out just because it ended up looking messy, so I just have these little lightning bolts looking like it's basically cutting off where the cable would be. But I have them labeled 1, 2, 3, and 4, of course 1, 2, 3, and 4. Now with RAID 5, we need a minimum of 3 disks, and the max, at least when we're talking from an operating system level, we have a max of about 32 drives. However, we're not really normally going to see, especially at a desktop level, anywhere near that. So typically 3 or 4 drives is going to be the max, maybe 5 drives in a very heavy-duty system. So with RAID 5, what we're doing is basically striping like we would do with a RAID 0, but we're also adding a parity stripe. So let's say, for instance, we wanted to write again. Let's give it a 512K file, just like we used in our previous example. Well, what we would do is actually stripe 64K across the first drive. Alright, so we would stripe 64K of data. On the next drive, we would stripe 64K of data. On the next drive, we would stripe 64K of data. And then on the third, or the fourth drive rather, we would write parity. And the parity is basically a mathematical calculation or an algorithm that calculates the data on the other 3 drives. So on our next pass, we would write data, data, again, and then we get down to this drive, we'd write parity information. So as you can see, for each stripe, it would be something a little bit different. So the next pass would be on this drive. The next pass it would be on this drive. So let's go ahead and just draw this out here. So as you can see, by doing it this way, we never have the data for each stripe that we take when we write. We never have the data and the parity sitting on the same drive. So that way, if one drive were to fail, let's say this drive went belly up, no longer there, well, we could put a brand new drive in there and we could reconstruct the data, because on this one we actually have the three stripes of data that we could recreate the parity information. For the next pass, we have the 2 stripes of data and the parity, so we could extract out what this must have been. Same thing for this pass. We have 2 passes of data plus the parity, so we could extract out what that stripe of data must have been. And the same with this. We have 2 stripes of data and parity, and we can extract it out again. So it allows us to slap a new drive in, let it rebuild, and again, from the parity information that's available to us, we can regenerate the information on that drive. Okay, now just to recap briefly about RAID, we have serial ATA, or SATA drives we can use for RAID. We also have parallel or IDE drives that we could use in certain RAID arrays. Now that's going to be at the desktop level, and that will be typically controlled via software. However, if we have a choice between hardware and software RAID, as I stated previously, we should always choose hardware RAID. And that's because it takes